Okay guys, today I'm going to talk to you a little bit about Ampere's law and calculating the magnetic field for a basic current carrying wire, a wire that has current I. So first let me just tell you a little bit about notation. If you see a circle with a dot in it, that means the vector is coming towards you. If you see a circle with an X in it, that means it's going away from you. And if you have trouble remembering that, think of it as like an arrow. If you see an arrow coming towards you and you only see the tip, you only see that dot. If you see an arrow going away from you, then you see this X. And so hopefully that helps. And so when I put this notation here, I mean the magnetic field is going into the page right here, and then it's going around in a circle, and it's coming out of the page here. So hopefully that tells you a little bit about the notation. Ampere's law, let's get to Ampere's law now. This is Ampere's law, pretty much. It says the closed loop integral of B dot dl is equal to mu 0 times I penetrate. And in a few minutes I'll tell you what I penetrate really means. But pretty much mu 0 is a constant, dl is a little segment of your Amperean loop, which I'll talk about in a minute, and B is just the magnetic field. So the way we apply this is it's kind of like Gauss's law, except for magnetic fields. And so instead of a Gaussian surface, which is three-dimensional, we create what's called an Amperean loop, which is more or less two-dimensional. And in this case, it's a circle centered on this wire here. And the reason we do that is for reasons of symmetry. Just like Gauss's law, if we don't have symmetry, we can't really use it to solve problems. So here's our Amperean loop. It's just a circle centered around this current carrying wire, and we attach any surface to it. It could be it could come out like this and be like a paper bag or something. In this case, it's just a flat surface. And when I say a flat surface, I mean think of a hula hoop, dipping a hula hoop in soap, and when you pull it out, it's got that film there in between. That's a flat surface. So that's what I've chosen for my Amperean loop. And when I say I penetrate, I mean the current that pokes through my surface. And so in this case, this current carrying wire is poking directly through the middle of my Amperean loop. And so for reasons of symmetry, if that's the case, the magnetic field is the same anywhere along the circumference of this loop for reasons of symmetry. Hopefully you can see that. I don't really know how to explain that. But if b is constant over this integral, then we can pull it out of the integral sign and just integrate over dl. That's actually a closed loop integral. Just integrate dl over our loop. And basically all that means is we find the circumference of our Amperean loop, which is obviously 2 pi times big R. And so this leads us to the magnetic field being mu 0 times I penetrate divided by 2 pi R, where 2 pi R comes from the integrating dl over our Amperean loop. So that's pretty much the easiest example I can show you of how to apply Ampere's law to a current carrying wire. And there's other situations in which we can apply Ampere's law, but I'll talk about that later on. And just ignore this stuff right here. I was trying to do something and it didn't fit, so I had to move it up here. But that's how Ampere's law works. Hopefully that helps.